guys, welcome back to the Physicate channel. In this video, we are going to continue again with our derivations in electromagnetism. In this video, we are doing now a derivation that is important. That's derivation number 3. It's one of the fundamentals that one must learn before they proceed with electromagnetism as a theory. This is called Stokes Theorem. Okay? So with regards to Stokes Theorem, there are a few things that we must also mention as we are going to proceed. The very first of all that is to say that, again, we will be working in rectangular coordinates. This is, of course, a first and quite easy coordinate system to discuss before we get into the fundamentals of what's happening. So this is the x, y, and z that we're considering. So before we actually begin with the derivation, there are certain things we have to state or start by doing. So the first of these is to say, let us define the curl, right? So what the curl is. So we're going to consider the curl of some arbitrary field in space. And this particular arbitrary field can be given by the vector, all right? Let's maybe say this is a vector A, right? And of course, since the rectangular coordinate is ax, ay, az. And this particular vector field acts on some arbitrary surface, right? So imagine there's some surface which exists in space, and there's an imaginary field that acts on this imaginary surface. Of course, this could represent a real system, a real event in space. So let's then say the curl of the vector A is given by the following expression. It is the limit of some surface, and assuming this surface goes to 0, in the limit that the surface becomes so small, and with some elements from I to 1. What are these elements? With some closed loop integral of the vector A with respect to some particular, path, right? And divide this by some surface vector Si. So what do we see from this particular definition? This is a fundamental definition of what a curl is. So from this fundamental definition, we see from the top, from the numerator, we have some closed surface because we used a closed surface integral. But then we also see that from dl at the bottom, we have some path, right, dl, which is enclosing or bounding a particular surface. So the path and the surface are coupled. That's what's important from what we see from the definition of a curl. Okay, now that we've mentioned this, it's very important for us to then consider the other things that will let us define or to begin the particular derivation. So let me make it a bullet point before I continue. So this is the bullet point 1. Then bullet point number 2 is that we shall consider small surfaces. We don't know what these surfaces could be, but we're going to consider small surfaces, and we're going to call these particular surfaces delta S, all right? Some change in S. So we're going to use a vector to describe it. And so we're going to have some delta Si, and say this vector of the surface goes to 0. So we're going to say in the limit that we make these surfaces so small that whether or not the surface in question is a cube, a square, or some weird shape, we are considering when you zoom into small surfaces. Then we say that dl, the path, bounds this particular surface delta Si that we are saying we are considering. So there's a path bounding this particular surface. And then finally, we must define what kind of vector are we dealing with. Of course, we said we are working in rectangular coordinates, so it then suffices for us to then say, let the vector field that we're dealing with be A, of course, as we've already defined it, but A vector is going to be some x component of A in the x direction, plus some component of A in the y direction, plus, of course, some component of A in the z direction. So these are very important things we're going to consider as we proceed with our derivation. Then with all this in mind, let us then say, we are going to again do a similar way, right? So a similar way to visualize it as we have done for the divergence theorem. So let's then consider some x component. Also, we've got the x component. We're also going to consider the y component, right? So we want to see the effects that we have, that curl, how does it affect the surface on the x component, the y component, and of course finally the z component. So we want to see the effects of this particular vector field line on these different components. Okay, so that's important for us to note. So let us, for these different situations, draw some Cartesian plane. So let us have this Cartesian plane in pink for all of them. All right, so let's have for the z-axis as well, so for the z component as well, the same thing. So we've got some Cartesian plane that we draw there, and we do the same thing, of course, for the y component. So we want to see how it changes from one component to the other component. And then once we've defined this, we are going to see how do we want the vector field to act. We want the vector field to begin from the negative to the positive side of the component in question. For the x component, it should start from the negative and go in the nx direction, which is the positive direction of the x component. Then we've got the same thing that we're going to consider for the y component, right? So we're going to have this vector field coming from the negative y component going to the positive y component, and we say that direction is the ny hat. Okay, so then we have got the effect of A in the AZ direction. This also affect in the NZ component of this particular direction. Then once you have this, we label, of course, our X hat. We also then label our Y hat and Z hat. So we do that for all these different Cartesian planes that we've just now drawn. Okay, now that we have those particular directions labeled out, we may then proceed to draw the small surfaces in which we see a curl acting. Okay, so we see that the curl obviously is going to act in an anti-clockwise direction, right? So anti-clockwise direction, that's how the curls are going to be. So we have a path 1 parallel to the y-axis, parallel to the z-axis, anti-parallel, etc., etc., etc. So there'll be 1, 2, 3, 4. And in the x component, we have the same situation, anti-clockwise. In the y component as well, we consider the surface on these particular different directions or different sides. Then, of course, finally, we have got the same particular curl that happens, of course, in the z direction, and it's going to also act anti-clockwise in its motion. So we're going to label this particular lengths 1, 2, 3, 4, and 5. So we've got that 1, we also have a 2, we also have a 3, and of course, we also have a 4. Okay, so that's perfect. Now, we've got all these different things defined. What's then important for us to see is how then is the curl acting. So for surface 1 on the x component, we see, okay, before we do that, maybe let's call this surface some ds, right? And in the x component, it's actually the dz component multiplied by the dy component. And this surface is a vector that's pointing, of course, in the x head direction or the nx head direction. So we see the same thing happens in the y component. There's a ds vector, which has got the dz, the dx components being affected. And this is pointing, of course, the first one is at the nx head direction. Then we've got the same thing for the second one is the ny head direction. Then, of course, we see the same thing for the last one. We're going to call it another ds, some element of area, right? And this is going to be some dy multiplied by some dx, acting, of course, in the nz direction. So dx multiplied by dy in the nz head direction. Okay, so that's important. Then we consider then the curl that we are considering here, curl of A in the n head direction. So for surface 2 in the x component, we see that the curl going up is simply and straightforwardly just a simple number, or maybe not quite as simple. It's the effect of AZ plus the partial derivative of A and how it affects the z component with respect to the y component, all that multiplied by dy. Then we have got path 3 is just straightforward, of course, but not quite as much, but it's the negative side, comes from the negative part. It's ay plus partial ay divided by partial z, all that multiplied by dz, okay? And then once we have that, we see, okay, the other one is just going to be straightforward down because it's with the path. So it's just negative az, and of course, path 1 is also the same thing. It's just going to be plus positive ay, okay? So that is quite fine. Then we have done that for the x component. We can also do the same thing in this situation for the y and the z component. So for the first of all, the y, we see the one going up is just also nice and easy. That's plus az going up. And the same thing can be said of path number 1, which is just straightforward here as well as the negative ax. However, path 4 is a bit different in that it is negative ax plus partial derivative of ax divided by the part, or with respect to z, which is that value there, all that being multiplied by the full derivative of z, so dz. In this case, it's dx, rather, dx and dx. Then, of course, part 3, we can do the same thing and say ax, a component in the x direction, plus the partial derivative of ax with respect to, now in this situation, the z component, multiplied by the full derivative in the z direction, or the full derivative with respect to z. Okay, so that's fine. We also then proceed with looking as well at the z component that we have at the bottom. So we are going to say that for the z component, the same thing is happening in that we've got for path number 3, we start defining that one, and it's going to be negative partial ay plus the partial derivative of ay with respect to x multiplied by the full derivative of x, or dx. So that's path 3. Then once we have defined that, we also go on to define path number 4. And path number 4 is also straightforward in a way again, but it's the negative side of ax plus the partial derivative of ax with respect to y, all that multiplied by dy, the full derivative of y. Then the other two, of course, are just going to be single letters or single expressions. So for path 1, we simply have the negative direction, but it's going to be ay. Then, of course, for path 2, we'll then have positive ax. So these are all the important things we need to talk about, how the curl is acting on these different surfaces in the x, y, and z components. Okay. So now, using these diagrams that we had at the previous page, or the previous slide, we can now go on and describe or compute the curve. So using the diagrams of the previous page, we now compute the flux, right? All right. So I think the first flux we're going to do it in components. That's how we're going to do it. So we'll start with the x component, then the y component, and of course, finally, the z component. Okay, so to begin with, we are going to consider the first curl, which is in the x direction. So let's then say curl of the vector A, its component in the x direction, and how it affects the nx hat direction. So ax dot nx in the x direction. This is going to be the following. We first know that by definition we said it is the closed loop integral of the vector A with respect to dl. So you have to take the vector A, multiply that by an element of length, then take all that divided by the area element, so ds. So this then gives us the following result. So we had for the first one ay multiplied by some dy, then we also added to this some az multiplied by some dz. Then we also added to this the partial derivative of az with respect to y multiplied by the partial derivative, or the full derivative of dy and dz. Then we subtracted from this particular expression some ay multiplied by dy. So we then write that down to be negative ay multiplied by dy. And of course, we've got other terms, like, so we've got a negative partial derivative of ay with respect to z multiplied by dz dy. Okay, that expression. And of course, we subtract from this an az multiplied by dy. So this is what we are getting from all those labels that we put on our diagrams. We are now combining everything. And of course, the element of area for the first surface was ds equals to dz dy in the nx direction. So we put that over there. But we notice something. Certain things here are definitely going to cancel out. So we see that from this particular first diagram. So we're going to do the same thing for the others. I won't be going back. But we consider these expressions, added them together, multiply them by the particular area as well, or the dl with respect to that area there as well. Okay. So that is fine. we then see that certain things will cancel out. So the ay dy will cancel out, az dz will cancel out, the dz dy will cancel out both at the top and the dz dy at the bottom. So all those other expressions will definitely fall off the integral, leaving us only with the partial derivative of az in the ay and with respect to ay or with respect to y, minus from that ay with respect to z, and all that, of course, in the nx hat direction. Okay, so we will label this equation number 1. Okay, so that dz you see at the bottom, that nx hat could have been outside of the whole fraction and not necessarily the bottom like we wrote it. So that is also something to note. Then we are going to also compute the curl of ay with respect, or as it affects the direction in the ny hat direction. Okay, so the curl of y in the ny hat direction is going to be, of course, ax multiplied by negative dx. Then we're going to add this to this, az multiplied by dz, ax multiplied by dx. Then we add to that, or maybe we also subtract before we add. So let's see if it can fit. Okay, let's just add to that the partial derivative of ax with respect to z, all that multiplied by dz dx. So the same thing we did on the previous page, we are doing it here, where we are adding those particular curves that we found, or those dl's that we also found. Then from this we subtract az dz, and then we've got another one, negative partial derivative of az with respect to x, and we multiply all that with respect to the dx dz. And again, we see certain things will cancel out, so maybe let's take all that, divide that by dz dx in the ny hat direction. We could have put the direction not necessarily at the bottom, but outside the whole fraction. Okay, then we see certain things will cancel out over here immediately. So that ax negative dx will cancel out with that ax dx over there. The az dz will cancel out. The dx dz will cancel out both at the top and at the bottom as well. So all those terms pretty much disappear, leaving us then with the curl of ay, of course, in the ny hat direction. Can then be written simply as this expression, the partial derivative of az with respect to z, minus the partial derivative of az with respect to x. So that was these are the expressions we finally end up with. So I think the top one was supposed to be ax and not necessarily az. So yeah, that becomes ax, and then of course that one becomes az, not az as we have it on the top there. Okay, so that's good. We could call this equation number 2. Okay, now that we've noted this out, we can then also proceed with the second one, or the last one rather, the last curl. Okay, so now we're going to consider the curl in the z direction, right? So we say curl of az in the nz hat direction. All right, so we've got that particular expression. We say all that is going to be equal to the following. On the numerator, we've got ay multiplied by dy, negative of course, plus ax dx plus ay dy. All right, and we're going to then say from this, maybe let's add, let's subtract. Let me just subtract the other ax dx that we have at the, which is left, the last one. Then from all that, we then add the partial derivative of ay with respect to x, multiplied by dx dy. Then we also subtract ax with respect to y, multiplied by dy dx for this expression. Then all that is going to then also be divided by dx multiplied by dy, all that in the nz hat direction. And we see the same thing again, things are going to cancel out here. So we see that the first expression, ay, will cancel out with the other expression, the third expression, the first, second will cancel out with the fourth, then those dx, dy will cancel out from the top and at the bottom. Finally, we are left with the curl of az with, as it happens in the nz direction, and that's going to simply then be the simplified expression, and that is the partial derivative of ay with respect to x, and all that is subtracted or subtracting the partial derivative of a with respect to x, ax with respect to y, and all that is multiplied by the nz hat direction, because the curl is actually a third vector. It has a particular direction. All right. Of course, here we're saying curl in a direction, not necessarily we're saying it's a dot product. You just say curl in the nz direction. So this is equation number 3. So it's very important for us to then mention a few things here, or to mention this. These are the partial rotations or partial curls. For us to compute the total rotation, because a curl is a rotation of a field, right? So it is a rotation, or we can just simply call it a curl. For us to compute the total curl, we have to consider equation number 1, equation number 2, and equation number 3, and we add them. So add 1, 2, and 3, which are the equations that we labeled on the previous page. So when we do so, we then arrive at this particular expression that we see over here, that the curl of A as a vector, right, is then going to be equal to, right? So the curl of A as a vector is simply going to be equal to the following. So the equation number 1 gave us the partial derivative of AZ, right? AZ with respect to y minus the partial derivative of AY. So that one is supposed to be AZ, not just partial Z. And then minus the partial derivative of AY with respect to Z. All that in the nx direction. Then we add to this the partial derivative of AX with respect to partial derivative of Z. Minus the partial derivative of AZ with respect to X. All that is in the ny hat direction. And then we finally add to that the last expression, partial derivative of AY with respect to X, minus from this expression the partial derivative of AX with respect to Y, and all that was happening in the nz hat direction. Something is important that we must also note. By definition, the curl is given as the gradient cross-producted by the vector field A. So by definition, we have that the curl can be given by nabla cross-producted by the vector field A. And we see that if we do that, we get the same expression on the left-hand side that we have with the partial derivatives and all the directions involved. So in other words, we can say this expression is equivalent to what we have on maybe the right-hand side in this equation. So the left-hand side is then giving us the right-hand side. So because of this, we simply can write then the whole expression anew as follows. The cross product, or nabla cross producted by A, which is then the curl of A, is given. I mean, we have to say something about A as a vector. We said A was a vector that was acting in the n hat direction, right? So n hat, and of course we split that n hat direction into nx, ny, and nz. So we've got the curl of A is the same as having nabla cross producted by A in the n hat direction, and we said all that was then equal to the closed loop integral of the vector field A dot producted by an element of path dl, and all that was divided by some element of area ds. But let's now say something about that ds. We're going to say that ds is actually an area field, or some dA, right? And it's an area, so that's what they're saying, an element of area, that's ds. So we can explicitly say it, so some area in a particular direction. Okay? All right, so now we've mentioned that, we can then see that even that ds at the bottom there, the same ds can be written, maybe we could even transfer it from the right hand side and put it the left hand side, and then we arrive at nabla cross-producted by the area vector A, which has of course its own direction, right? Of course that dA is in the n hat direction, so we could have that area vector A dot producted by this particular ds, right, as a vector. Could be the same as simply writing that nabla cross producted by this vector field A, which has a particular direction n hat, as we already mentioned, and all that can then be dot producted by some ds, which again is in the n hat direction. So we want to find an expression that we can use to take this whole expression and maybe arrive at this fundamental law of Stokes. So we can say that this is then simply nabla cross producted by A, and all that is happening in some element of area ds, right? So some dA. So we say all that particular value dot producted by this dA. So we now have a scalar on one side, and also we can have another scalar on the other side as well. Okay, so now we've got this particular equation that we can write, which is the nabla cross producted by this area vector, and all that is dot producted on this particular area dA, and we say all that is equal to the closed surface integral of A in a particular path. So some A bounded by a path. And this expression that we have now arrived at happens to be what is called the point form, because we are talking about a single particular surface, right? So a single particular surface, and we describe how this surface has got is bounded by some path, right? So some path is bounded, some area is bounded by a path dl, and this is the point form of Stokes theorem. So it's not general yet. To generalize this to any physical system, because physics is all about physical systems that are generalized, and you want to have an equation that can describe pretty much any system. So to generalize this, let us consider some open surface. So an example of a surface we can deal with in this situation could be some half sphere, right? Some half sphere or anything of that nature. There's no restriction on what surface you can have. So for example, we're discussing some half sphere. So in a diagram, this would look much like something like this. We've got some bottom part of some hemisphere, and we say this hemisphere happens to be hollow. So maybe let's say there's like an inner part as well, some thickness to this particular sphere that we've just drawn. But we want to look at the surface of this particular sphere. What's happening on the surface? So let's split the surface into some squares or some parts. So let's put some longitudinal lines and some equators around this particular line. So something like the Earth, right? So we've got these particular lines being put there. Then in this surface, this could be thousands and millions of squares that we've just drawn. But let's focus only on this section. This section can be rewritten. If we zoom into these particular surfaces, we have that it is some random, squares that we have, or something that looks square-ish, and we can separate this and write them like this. So we've got those particular surfaces. Then we look at how these curves that we said are acting. So we draw some anti-clockwise curves to begin with. So on every surface, there's some anti-clockwise curve. So in that particular surface, we've got an anti-clockwise curve. On the one at the bottom, we also have another anti-clockwise curve that is also acting. Then we see the surface at the bottom, we only have one line. The one at the top, we have another one line. All the other ones on the sides are going to be, of course, opposite directions to the one adjacent to it. So there are also going to be some directional curves that we also can see. Okay, so another thing that's important here is that we can say, let us say that this particular surface that we are now just putting a line on, let's call it the nth I surface. And the one before it is n minus 1. So nth minus 1 I, or nth I minus 1 surface. All right, so we're dealing with millions, and we just chose 2 at random. Let that surface be S. So that's our surface we're dealing with, some volume, and we're calling it S. Then once we have that, it is then important for us to then see something that's happening with the field lines over here. We see that those particular curves that we have just drawn there, this curve cancels out the other one, they cancel out, these ones cancel out on the sides, they're all adjacent. These two cancel out each other, these two cancel out each other. Pretty much all curves are cancelling one another. But the ones at the surface of this particular sphere, the open part, these ones remain. They have got nothing that's cancelling it because we cut out the other half of the surface. So only these particular fields, right? Field lines. So we are saying those are field lines. So these field lines on the surface, right, or at the edge of this particular surface remain. Everything else pretty much is gone, right? It cancels out. So you can maybe write that down to say that, okay, those field lines that we've just indicated in black, all these literally cancel out. Those are all field lines that cancel out. In other words, they no longer exist. So these field lines are curling and they cancel out, but the ones at the edge do remain. Okay, we write that down. Then we also say something that's also important for the generalization. Let's say that's the small area, S. But we want this S to be so small. We don't want big and huge small areas. So let's let this go to 0. Then the number of these particular surfaces, we say let them be infinity. Let them be so many. We don't want to be able to count them. So Ni goes to infinity and delta Si goes to 0. Now that we've written all this down, we can now go ahead and say, of course, after doing this generalization, for us to then see or realize it, we have to sum up all these parts. So, summing up all the parts with the field lines that remain, we will arrive at the particular equation that we are going to write down below. All right, so the equation is the summation of the ith surface from 1 going to n, multiply of this summation of the nabla A, which could be an AI, right? Nabla cross dot AI dot DAI, all right, plus the summation from I again going to n of some epsilon. So it could be some number of delta SIs. So some epsilon SIs. All that is then going to be equal to the summation from I going to n, and we sum over that particular closed loop integral of A bounded by this particular path Li. And we say Ni in this situation, we want it to go to infinity. In other words, the number of surfaces increase to infinity. Then we see this particular surface that we have there are all the other particular field lines that we had before, and we saw these ones were cancelling out. So the field lines produced by these surfaces all cancel out, leaving us with the final expression. And this is the important expression that we wanted to find in the beginning. So the integral over S, that particular surface, so in other words, this is immediately going to be an area integral, which is going to be the nabla cross producted by A, which is the vector field, dot product this with the area vector, is going to be equal to the last expression, the closed loop integral of A acting, or this particular area, this particular vector field bounded by some path dl. Of course, there's also going to be another area vector or some length vector S. Then we see that this boxed equation, ladies and gentlemen, this is what we wanted to find at the beginning. This happens to be Stokes Theorem. And Stokes Theorem is quite a very nice and fundamental theorem, because what it says is that we have some surface integral on the left hand side, where the dA is of course an area, and this should give us a scalar value. And the closed path dl encloses this particular surface dA. So the line integral and the path S yields some cross product between the gradient or the curl of A, gradient cross product by A, which gives us the curl of A, around the entries of the surface surrounded by some vector field. Okay, so this is very important because there are many applications that we can use where we relate some area with a path. We saw in the previous one, divergence theorem was relating some particular volume to an area. So now here we are now able to relate some particular surface to some particular path. It is very important, ladies and gentlemen, that you subscribe to this channel so that we can have more energy to make more of these videos, more of these derivations. So see you on the next one.